what's one really nice thing we want to be able to do with our linked list? Can you name one for me? What would be a nice function to implement for our linked list? What do we want to be able to do with our linked list? How about that? Add? Yeah, so add something would be really useful. We want to be able to add nodes. What else do you think we want to be able to do? Delete. Delete nodes. What else would be really useful? Yeah, find or check to see if there's a contains. What else would be nice? Update. So we could potentially want to find some value and then change the node value. That would be more of like a method on the node data structure, but you could probably want to do that. So that'd be one to have potentially. I don't think that we're going to per se use that though in the homework, but that's like a good optional one we could potentially include. And so this is actually one of the things that's interesting, is that you could potentially need extra methods for what you're using this for. It's all going to be implementation based, really. I tell you this much right now, you're not going to use this update, or you shouldn't need to use an update for the homework 3. But that's something that you could potentially want to do. Is there something else that you think you might want to be able to do with these things? Switch nodes, that would be a good thing that you might want to do. In our case, I don't think, in homework 3, I don't think you'll need that, but you want to potentially be able to swap nodes. So, optional swap. Anything else? Like you could go on and on, right? And you could go ahead and have like something that deletes the entire list. We have something that creates a random list. We have something that inserts at the beginning, because there could be a difference between inserting it at a sorted value. We have something that inserts at the end. We could want to delete something at the beginning. If you want to delete something at the end, we could want to delete by a value. So there's a lot of different ways that you can go about doing some of these things. And so there's like a lot of different ways you can do this, like first, last, location, and then this could also be first, last, by value, or potentially by all values. Like there's a lot of different ways you can go about doing that. So this is like the general like linked list data structures you could want to have. Now, when it comes to actually putting this on paper, though, you really have to think, what are you going to be using this for? And so one of the common uses of the linked list is what's known as implementing a stack. There's a second data structure that's equally as common as the stack, and it's known as the queue. We're going to be covering that later on this week. But the stack is very simple to think about. So I like to give an analysis of cleaning plates. So suppose you and your friend are working to clean a set of plates, and maybe you have several different people that's working. Maybe you have initially a stack of plates that are all dirty, and then someone's maybe washing the plates, and then next to them are all stack of plates that have been wet, and then you have someone that has a stack of plates and they like scrub it off or something. You're like, I have no clue how you clean the dish, and then another person works on drying it. And so what happens is there's like these stacks in between. And now it would be very dangerous for like one of your friends that's helping you clean your plate to take like a plate at the bottom, right? That would be kind of a silly thing to do. You might accidentally pull off a lot of plates from the counter, and then you have to buy a whole bunch of new plates. The good news is that they'll all be clean, so you kind of did the job indirectly, but not really. So that's like one thing you want to consider. It's like you don't ever want to take off a plate if it's not on top. It's very easy to access the top plate, and it kind of gets a little tricky to access the middle plates, because in order to access the middle plates, you have to create a second stack. And then you have to take that plate and then you have to merge the stacks back together. And admittedly, that's an operation you might want to do when you're doing stacks, but you won't need to do that in this problem here. So you should always access only the top element. And then additionally, when you're putting plates on the stack, do you put them at the bottom? No, you don't want to put them in the bottom. You don't want to put them in the middle either. You kind of want to put them on top. Now, I know my friends have a whole bunch of different varying types of plates, and so it's really annoying because if you want them to look really nice, you can't just put them all on top of each other willy-nilly. So I end up having to do this like really terrible thing where I like separate them very barely and stick a plate in there, and it makes this horrible glass on glass scratching sound. So that's like, I guess, a really bad example because I'm lazy. But really, you should only ever try to put elements on top of the stack or you should go ahead and try to remove elements from the top of the stack. You should never be messing with any elements that's not the top. And so let's go ahead and talk about linked lists and potentially figure out how we can use a linked list to implement one of these stacks. So it's very simple to explain, right? You always will mess with the elements on top. You'll never work with any elements below. So it shouldn't be that hard, like description-wise, to get this to work. We'll find out. So does anyone have any idea? Yeah, there's a question on the back.
I was just wondering if you could zoom in a little.
Zoom in? Yeah, let's try doing that. Autofocus. Is that better?
Yeah, much. Thank you.
All right, no problem. So the question was, how can we use a linked list to make a stack? Ah, nice. All right, so you're a little bit familiar with these terms. Yeah, so you can call it FILO or LIFO. Either one of those is technically correct. It's either you call it the first in is the last element out. And that makes sense because the first element on your stack is always going to be the bottom element. And then if you put 17 more things on top of it, it's going to always be the last thing of the elements that you end up removing. So it's known as like the first in, last out, or what's known as the last in is the first one out. The last element you put on your stack will be the first one that you take off of your stack when you're taking elements out. So, I mean, that's something we can go ahead and put up here. It's the last in, first out, or first in, last out. The queues is basically the opposite. It's going to be a FIFO, which means first in is the first one out. And that makes sense from a lot of standpoints. The stacks, I think, is probably a little bit harder for people to conceptualize sometimes. But what's something interesting? I'm actually kind of curious. Who here remembers me talking about stacks earlier in the class? Because I have talked about them before. Do you remember what I was talking about them with respect to? Like, what was I using them for? Yeah?
Memory.
Yeah. When I was talking about memory, I was saying that we have a stack of memory, and I was saying that we have a heap of memory as well. And so when you're using the stack of memory, what's going on is you're actually like doing recursive calls, and your recursive calls are actually putting like snugly against each other at the top of memory. And so when you're doing your recursive calls, the last element that goes into your recursive call, or the last function that's called, is the first one that ends up getting resolved. And so that's like one way you can help conceptualize it a little bit if you really understood recursive methods. If you don't understand the recursive methods, you can ignore the last 2 minutes I've been talking a little bit. But I think that if you know recursion, like stacks will hopefully be a nice segue. Like the recursion will be a nice segue into stacks. But anyways, so how do we use a linked list to make a stack instead then? That is a really good question. Because I asked it. All right. So we know that our linked list has like these boxes that are pointing to other boxes. So I think that it would make sense if I said that we only want to either put elements on one end or the other element, the other end. We wouldn't ever want to put an element in the middle of our linked list because the stack should only be operated on one of the ends. Do you guys have a preference of working on the front or the back of the stack? You want to work on the back of the stack? Back of the stack. All right. That's not fun, but okay. So we could then insert elements always to the end of the linked list. And if that's the case, what you can think of as that means that this would be the top of the stack. Because if you always insert elements into the end of the linked list, you always are supposed to put elements on the top of your stack. And so that means the element that's going to be highest on your stack is going to be whatever the end element is. When we're removing an element then from the stack, where do we remove this element from? From the top, which would be what with respect to the linked list? The tail, the back end of the linked list. So we always would remove an element from the back of the linked list. When removing elements from the stack, I put it in quotes because this is actually a linked list. We remove from the back tail of the linked list. All right. So one thing I probably should have said earlier, because it'll make describing this a lot easier when I'm doing my lecture a little bit from now, where I'm actually doing an example of this, is whenever we insert an element into the linked list, this is known as a push operation. And then whenever we remove an element, or not from the linked list, but from the stack. So this is for stacks. And then whenever we remove an element from the stack, we're considered popping it. So what else is something we might want to be able to do with the stack besides pushing and popping? Yeah? Yeah, so that would be another really good operation. We didn't have that before in our list of methods. Let's go ahead and add that real quick to the data structure. So like maybe a size or empty. So how could we check to see if the stack is empty? You're not wrong. In fact, that's exactly what I would do, is I would go ahead and check to see if something's null. But the real question is, what are we checking to see? What are we checking for null? And the answer is it depends on your implementation. And so you do want to go ahead and do check for null somewhere. We'll go over that detail a little bit later in class when I try to code up a stack. And I say try because I hope I can code it up in the time I'll have remaining at that point. So we will do a null check, but it depends on the implementation a little bit. Alternatively, what you could have, and this would be really nice, is inside your stack data structure, not only do you store the node, you store these pointers, you store the head and stuff like that, you also can store a size variable. And if you ever see that the size variable is 0, then you know that your stack is empty. And that can help you out as well. So optionally, you could have a size inside your linked list, and then that's just like one extra parameter. However, doing that can be a little bit funky because that means you need to make like a full-blown struct for your linked list, and then you make a full-blown struct for your node, and so you have to make 2 structs. And some people have difficulty making just 1 struct. So that might be a little bit too advanced. We'll see how well we're able to do that in a little bit from now, but we don't necessarily have that ability. So if you want to code it that way, you can, but it's not always in there. And so it really does depend on the implementation. So let's see. What else could we potentially do? Is there something else that we might want to do with a stack aside from checking to see if it's empty? Like, is there another function you can think? So we have the push, we have the pop, and then we have the empty function. Yeah? So that could be really useful. I'll tell you this much though, you won't need that for the homework assignment. So, but that is something you could want to do. And the reason why you would want that is if you're using an array-based stack. Well, since we're using a linked list stack, we won't care about the number of nodes for now. We'll worry about that if I get into the array-based stack, which I probably won't because I'm going to be doing just the linked list because that's what I want you guys to do on homework. I saw this hand, and I'll get back to you. What's up?
You would want to see what that first item is before you pop it.
Yeah, so before you remove that item from the list, maybe you don't want to do that. Inside the example, the program that we're getting in class, which hopefully I'll be able to get you guys some test data soon for that, because I want to get you guys 2 more cases that you can test on. Before you remove that bag, you might not be able to purchase it because you might not have enough money, and you might not be able to carry it. You might not physically have enough strength to do so, because there's also like a weight with these bags. And if you can't do either one of those 2 options, you have to leave the bag there. And so you want to potentially just look at the top element and then decide if you want to take it. And so this is what's commonly referred to as the peak operation. So check the top element of the stack. And this is typically referred to as peak for the sake of the stack. So with these 4 methods, the push, the pop, the empty, and the peak, you can actually do pretty much the entire homework assignment for the sake of removing items from these list of, from the bag things. The one thing that you might have difficulty with is actually outputting the elements in the right order. In fact, I recommend using a queue to do that, but you can get away without using a queue. You can actually use a stack 3 times, and you can effectively emulate that behavior, but that's a little bit crazy. So additionally, what you could have done instead is you could just use an array list, because I'm not forcing you to use a queue on the assignment. Like whatever you can do for output, that would be really nice. But after I go over these 4 methods, you should be able to code, I want to say, good 80 to 90% of the homework assignment. So let's go ahead and talk about how to actually do these methods then. So we were saying that we were going to try to insert these elements at the end of the linked list. So that's what we're going to try to do with our push operation. So we're going to go ahead and talk about pushing in the back. This is going to be a linked list. And for those of you that aren't aware, the tail means the end of the linked list. Normally you'll have a tail pointer if you're doing a queue. You don't necessarily need one if you're doing a stack. There's a question there, sorry, I didn't see.
Yeah, so I was thinking, is there a real use case for this? Like, say, a text editor like Microsoft Word or Google Docs use a stack in order to store, like, say, a redo or an undo? So, like,
Yes. Yeah, so that's like one way you can do it. So if you're looking for code uses, that's one way. Another thing that stacks are very heavily used in is when you're doing actual code compiling, because the parenthesis balancing is effectively a stack problem. Because you want to push open parentheses on the stack and you want to be able to pop them off. In fact, I'll go over how mathematics in coding is useful with stacks. Like stacks are useful for doing math in code. So is there any other questions about this right now? No? Okay. So how do we push onto the tail of the linked list? Well, it would be really easy if we had a tail pointer. So what we should store inside our stack or our linked list your linked list will probably always need a head pointer. So we'll need a head.
Professor, I have a question.
Yeah, what's up?
On the grading information for our assignment 3, it
Might be wrong. What's going on?
says use a queue to store the bag sold prior to printing.
Oh man, I'm an asshole. All right. Did I actually say that that's 10 points?
Yeah.
Okay. I'll probably end up removing that, and I'll just say 10 points for getting the right order, like at least one of the right orders, because I don't want, or have some method to try to do the right order, so that way you can go ahead and use whatever you want, because I don't want to force you to use a queue on it, because there's a way to do it with just a stack, and I think that some of you guys would think is really funny to just go ahead and code up basically only one data structure for this. So I'll change that. I'm really sorry about that. Thank you for letting me know, though. I'll fix that momentarily whenever I can work on that problem statement. All right, so our linked list will need a head because we basically always need a head. It's pretty much guaranteed. We're going to need a tail in this case if we want to be able to insert things really quickly, because if we have the tail pointer of our linked list, then all we need to do to insert something is just add something onto the tail and then move the tail over. So we will need a tail to do quick insertions. And now the question becomes, how do we do, so that's like quick insertions, or in other words, pushes. Now, how do we do quick pops, though, is my question. So when I pop an element, I'm going to go ahead and take the tail, and I'm going to remove it from the linked list, and then I need to somehow update my tail pointer. How do I update my tail pointer once I remove an element from our linked list? So yeah, we could use the temp pointer, but the issue is like how I've used temp pointers in the past is I always have like reference to the thing prior to it. And unfortunately, I don't have immediate reference to the thing prior to it. If I wanted to store this temp variable inside the linked list, and then I'm like, okay, now I have the temp pointer which points to the element before it. Imagine I pop one element, and now I want to pop this element. I don't have the temp pointer anymore pointing to the element previous. And so now I run into an issue if I try to double pop. So double pop means that I can't actually do a back pointer and then second back pointer. And then you'd be like, oh, let's use a third back pointer, like a temp 2. And then well, what if I do a triple pop? And so the thing is, I can just always say, well, however many pointers you have extra for referencing, I'll just go ahead and point, pop that many times, and then that's going to go ahead and break your code. And that will not be fun for you, it will be fun for me. So we can't, unfortunately, do this very easily unless we have a reference to the node prior. How can we have a reference to the node prior to a node? Doubly linked list. So if you want to do this with a linked list, you actually can't do this very efficiently. In fact, you're going to need the DLL rather than just the LL to do this really well. So And so this is kind of sad that we're going to need this for doing fast pop operations. And so that's why a lot of people end up not actually inserting to the end or inserting into the tail of a linked list to do a stack. They actually insert into the head of the linked list to do a stack. So this is, again, we're doing push on tail. And so this is like kind of a weird thing that's going to be an issue. Like hypothetically, I don't want to do a doubly linked list because I have to do like double number of operations whenever I'm doing an insert or remove. I don't really like that idea. And so instead, I'm going to go ahead and talk about how to do a different version where we're pushing on the head. That's not to say that you can't do this with a linked list. Again, all you need to do is have the doubly linked list part. And I did show how to do one of those in class, so that is an option. But this is what I prefer to do because it requires a lot less management and it's harder to screw this up. And I'm really good at screwing things up, so trust me, I'm an expert. All right, so now if we're pushing onto the head of the linked list, we know that we need to have a head. Missed the parentheses. All right, so it's a default requirement to have a head. Now, do we need the tail of the linked list? What do we normally need the tail for if we want to insert the end, right? But if we're inserting to the front of the linked list, you should never insert onto the head because you should only put things on the top of your stack. You should never put things onto the bottom. So actually, we don't really need a tail in this case at all. So awesome, no tail. All right. So the head allows us to very easily insert things into the linked list very easily because all we need to do is just say, okay, the new node that we're adding into our linked list is going to point to the head, and then we go ahead and make the new head the node that we point to, right? If we have, consider the push operation. So this is the old head. And then after push, maybe this is like A, B, Q. Bless you. And so after we push element z, we're going to have this new linked list. And so the old head, like you can just call it the head. The head is pointing to A, and then A next points to B, E next points to Q, Q next points to null. And then what we end up doing is we push element z on there. And so what we say is, z, your next value is going to be A, and now we go ahead and say the new head of the linked list isn't A anymore, the new head of the linked list is z. And so it's a very easy thing to do. If you have like an insert node pointing to here, then you don't need to worry about doing any crazy pointer manipulation where you break things. So I guess the wrong order to do this is if you move the head pointer first, then that's going to cause problems. So move the head pointer last is, I guess, the caveat of this. But you're going to need to do two pointer manipulations. One to have z pointing to the old head, and then one to make the head now z. So that doesn't seem that bad. And so now the question is, how do we pop something from the linked list? How do we get rid of z? Because that's like one of the second operation that we need to do it. And how do we do it quickly as well? Yeah, so we could do what we do with a lot of deletions inside linked lists, which is we hold on to the pointer that goes afterwards using some special variable, then we free the old pointer, and then we just update the rest of it. So in terms of popping, we have so what we want to do is we want to store the temporary to the new head. And the reason why we want to store the head first, the new head, is because if we freed A before we access B using this pointer, we would end up dereferencing something that's already been freed. Like we'd basically be doing a use after free. And a use after free would be really bad. So we want to first find out where B is at before we go ahead and touch this guy at all. Because if we touch this guy before we get to B, we might have some garbage written here, and that would be bad. So we want to first go ahead and get access to B, and then we'll worry about deleting A. But the thing is, we shouldn't just say, hey, the head is now equal to B, because if we move the head pointer to B, then we lose reference to A, and then we can't free it. So it's kind of like, we need to be very cautious with this. We can't just obviously free A, and additionally, we can't just move our head pointer to B. So we need to store it in a temporary value. So we have old head points to A, and then we have B, then we have Q, and we have null. And so then up here we have some temp. And so what you could do to get this working is you should say like temp is equal to old head next. And so that will have the next value that we're going to be using inside our stack ready for us. And so now we're able to just free the old head. So then you free the old head, and we have old head is pointing to some garbage memory. That was once A. This is pointing to B, which has the temporary pointer on it. And then we have the Q, which points to null. And so now that we've freed the old head, we can go ahead and update our head to now be the temporary value. So we update head to temp effectively. And now we have the new linked list of head is here, just pointing to B, and B is pointing to Q, and then Q is pointing to null. And so you don't have to worry about A anymore because A has been freed. And we don't have to really worry about dangling pointer because you can imagine if old head and head were the same variable name, then basically I got rid of whatever old head was pointing to. I don't have to worry about dereferencing something that's been freed already. So this is like kind of the set thing to do. It's a little much, but This is honestly not the worst thing that you'll see in terms of code for a linked list. In fact, there's something I kind of neglected to do here. What would be an important thing to do before doing this whole operation? Does anyone know? Yeah, check to make sure I'm not pointing to null. What if our head pointer is pointing to null? Like if our stack is empty, then we would have an issue. So we really need to here check for null. Without this operation, when you try to pop off of an empty list, you'll dereference null, and your program will crash, which will be great that you found that issue, but it will be bad if you submit that to a client or to me, because then you'll lose points or a job. I don't know which one of those is worse. What's up?
Or does that not matter?
So it actually won't matter, and actually it's really nice if temp is null, because if temp becomes null, then that means head is pointing to null now, and so that means our list became empty. Because if temp was null, then that means A was the last element in our list. Does that make sense? However, if the head is null, depending on what happens there, it could be horrible. Like it could be the fact that you were trying to do some counting thing and you needed an extra element and you didn't get it, in which case you might need to do some error handling. But in our case, if you ever run into a situation where you're trying to pop null, that means that you don't have a bag at that location to buy. So you don't have to worry about anything. You just have your car drive away and report the things that you bought. All right. What else? So this is popping. We did pushing. All right. So now let's just talk about, I guess, peaking. And I'm not talking about the city in China. Or is it Japan?
China.
Uncultured, I swear. All right. So how do we peak inside, how do we peak at the top element of our stack? Yeah, that's all you need to do. So the peak will always return the top element of our stack. So all it needs to do is just return the head. So you don't actually need to implement a full-blown function for this, obviously. But if you wanted to do that to make it like you understand what's going on, maybe you want peak to potentially update a value. You probably shouldn't do that. But it would be nice to go ahead and like just potentially, if you want to be like really formal, to go ahead and write out a whole peaking function. But really, you just need to return the head for the sake of our assignment. And for the sake of a lot of things as well. All right, and then the last thing, if we're checking to see if a linked list is empty, how would we do that? How would we do an empty function? Yeah. I even did the code for you guys. So just to check to see if the linked list is empty or the stack is empty, we just say, hey, is the head equal to null? If the head is equal to null, we return true. There's no elements inside our linked list. There's no elements inside our stack. We don't have to worry about doing anything else. So these are the 4 common functions you'll see in the stack. Now let's go over a simple use case on them. So who here knows math? Don't be shy, raise your hand. Not many of you? Well, I don't either. So this will all be an experiment for all of us, or something. Learning experience? There we go, that's the word I was looking for. Praise? All right. So when I'm talking about math, I'm talking about mathematical expressions. And has anyone ever heard the phrase, please excuse my dear Aunt Sally? Yeah, raise your hand if you heard that one. Does anyone have anything that's similar to it that they know of?
What is it?
Please excuse my dear Aunt Sally? Good question. So raise your hand if you haven't heard that before. A few people. Okay, that's all right. So please excuse my dear Aunt Sally. This is what's known as the mnemonic device, something to that extent anyways. And it's basically saying the order of operations when you're doing some mathematical expression. So what do you do when you do a mathematical expression? What's the first things you will perform or evaluate? Evaluate Sally. So when you're doing a mathematical expression, you will normally do the parentheses first. Then you do the exponent. Then you do multiplication. And normally you do division at the same time. We're not barbarians. And then you use addition and subtraction. And so we have the P for parentheses, the E for exponent, the N and D for multiplication division, and then the A and S for addition and subtraction. And so this is what I learned when I was in the 5th grade, I want to say. It was a lot of fun just doing math, like just looking at a set of numbers and doing it out. And there was like some Polish computer scientist that had to spoil the whole fun. He's like, I don't like the parentheses, and I just want you to say, excuse my dear Aunt Sally. And then we kind of ran into a whole bunch of ways that how do you actually remove parentheses? Can you remove parentheses and still be able to evaluate the function, or the expression, I should say? Like, is there an order in which you can write it such that you can go ahead and basically express the importance of a symbol without actually doing all of one type of symbol first? So these are like a lot of really high-level questions that a lot of you probably don't understand what they mean, and that's really okay. So the idea is, can we do mathematical expression analysis or mathematical, I don't know what we call, like just formula? Can we do math? That's the real question. Can we do the expression evaluation without parenthesis? And the idea is that we want to go ahead and just basically say the order of the operations, and the order is the way you do them. And that might sound really, really difficult. But as it turns out, there's like things called push-down automata that can help us with it, which you guys haven't learned about yet, because you haven't taken COT 4210? Yeah, question. Oh, there you go. Someone actually knows this. Yeah, so what we have at our disposal is what's commonly referred to as postfix notation. And sometimes people call this the reverse Polish notation. And when I first heard of the concept of reverse Polish notation, I thought it was a slam against people from Poland. But actually it's not. The person that came up with this way of writing this expression this way was Polish, and so they actually named it after his nationality. And I feel like they partially did it to do a slam on Polish people, but we'll go over that in a little bit. Not slamming on Polish people though, just the notation part. So how the reverse Polish notation works is a very simple method, which is as we're getting operations, we just go ahead and perform those operations of the last two expressions we've seen, and we go ahead and can repeat this process until we run out of operations and run out of operands. So the idea is, imagine we have A, B, plus. What this here would be inside Polish, this is like how you write in the postfix notation, A plus B. So this is like how you do a translation. But they can kind of do weird chaining things. So you go ahead and say A plus B, C star. What this would be is we do A plus B first, and then we multiply by C. And so now the question becomes, well, can we actually take any expression written this way and turn it into this form? And this is actually the form that a lot of computer programs will try to turn your expressions into, your math expressions, before it does computation. And the reason why is because this is a very easy way for the computer to do math. It's like, okay, we get this value, we get this value, we add them together, we get a new value. We take that sum, we take this value, we multiply them together, we get a new value. And then we might do something else with this. And you might be like, well, yeah, so that looks really well like you're taking some value and you're performing some operation. But what if you want to take one value and do an operation with it? You want to take another pair of values and do some operation, and then combine them together. Can we combine two things together inside this notation? And the answer is, well, yeah. So if we want to take two values, maybe we want to take a plus b, and we want to multiply it by c plus d. So we'll go ahead and write out what a plus b is. A plus b is a, b plus. C plus d is c, d plus. And then what we do is we always take the operation that we're going to perform this on, and we put it at the end. So this is what a plus b times c plus d becomes. It becomes ad plus cd plus multiplied. So the computer goes ahead and says, okay, we got a, we'll get b as well, we'll perform the add operation. Now we have this a plus b monster, I don't know what it is. And then we take c, and we take d, we add them together, because that's what this plus is. The operations will always work on the previous two values. And then we go ahead and take this value and this value that's returned, and we multiply them together. You can think of it as your computer will go ahead and take this and turn it into some value v1, and then we have cd plus, and then star. And then we'll go ahead and perform the operation on this, and we'll get some v2. And then with this operation, like with these things gone, when we perform the multiply, we just multiply on v1 and v2 to get some results. So this is occurring in the first step, this is occurring in the second step, and this operation is occurring in the last step. So what do we notice about these operations? What are they being worked on? It's a stack. Yeah, it should be if I'm doing a stack lecture, right? So what is the add being performed on? Like hypothetically, we work our way across this operation. We go to A, we go to B, we go to this plus sign. What do we add together? Why do we add them together? They were the last two elements. And then we have C and we have D. So that means we have V1, we have C, and we have D. And then when we get to this plus operation, what do we add together? We don't do anything with V1, right? Even though we totally have V1 like as a thing, we only add the C and D. And why do we only add the C and D? They were the last two elements that were put into our list of operations, or into our list of values. So we're always performing this operation on the last two values that we have seen. So A and B were the last two values when we got to this plus sign. Then when we got to this plus sign, the last two values were C and D. When we get to this multiply, it's after we've already performed whatever operations happens with this plus sign. What we end up doing the operation on is V1 and V2, because those are the last two elements that are inside our list of values. Because we go ahead and remove C and D and replace it with V1. And so really simple, how can we code this up? Yeah, there's a question over here.
Just, I guess, just to clarify, I guess, is it safe to say that once you hit like the operation with the plus sign there, you have to check the last two and then add those two together?
Yep. Yeah, question? Yeah, so that is a little bit of a caveat. So the thing is, sometimes you might want to do an operation that doesn't do last two elements. Like an absolute value is a really good example, right? The absolute value performs on one operation, it returns one value, right? It's not a binary operator, it's a unitary operator. And there's also sometimes three-way operators. There's something known as the triple product inside Calculus 3 that you guys have learned. Probably not. Okay, cool. So that takes three operations that you end up operating on. Most of the operations we do only do two. So exponent, you have like the base and you have the power, right? Or base and power. When you do multiply, you have one side, the other side. When you do subtract, you have the subtractant, and I don't remember the other one. When you have the divide, you always do A or B. When you have add, you only add two values. So yeah, in this case here, we're only doing two values because those are the only operations we're going to be working with. You can get this to extend to working with three values and even more, because the thing is the order is very uniquely defined here. If the order wasn't uniquely defined, then you could have issues when you do subtraction, because it's really important to know that 4 minus 2 is different than 2 minus 4. And we have that ability here. If you want to do That's a really good question. If you want to do 4 minus 2 here, like I say 4 minus 2, but how it works in postfix, so because you normally do it this way. So if you want to do A, B, if you want to do A minus B, you do A, B minus sign. Does that make sense? All right. So let's see if I can code this up in 25 minutes and then work on the second part. Yep. CS1. Code. Folder week. So this is going to be a lot of fun because not only do I have to Cool. So not only do I have to do the whole calculator bit, but I also actually have to code the stack part of this. So that's going to be a lot of fun for me. All right. Now that I think about it, I should probably get this on the right location. So cd dot dot cd code. Why did I hit tab? Alright, that was awesome. I don't know how I got that to happen, but alright, so now you can see everything I'm doing. This is a text file. Let's rename that. Say this .c. Cool. All right, so now I can actually see the color scheme. So we're going to need standard lib. I want standard I/O. It's one of those days. All right. Pardon my Java. All right. And so I need to go ahead, I need to make some way to go ahead and store these numbers, and then I need to be able to access them when I need to get into them. So what I'm going to do is I'm going to write a really simple, a really dirty stack. So I'm going to make a struct node star, node, not node star. It's going to have a value associated with it, and it's going to have a struct node star next pointer. And so I'm going to go ahead and make a function. I'm going to typedef this to make my life a little bit easier. Whoa, I can do that? Mind blown. All right. And so I'm going to go ahead and make a int pop, and it's going to take in a node star. And then I'm going to have a node star push int val, just int. And then I'm going to go ahead and I don't actually want to check to see if it's empty or if it's not. I don't need to do that because I'm going to assume that I'm giving myself a valid expression. However, you could write some code that checks to make sure it's valid as well. But I'm going to assume that it's all okay. And all this is going to be doing is it's going to be figuring out what the value is for some postfix expression. So let's go ahead and do that. So int pop node star, this is going to get the head. And all it's going to do is it's going to return, oh no, I need to do two things in this. Darn. Okay. So this is not going to be pop, this is going to be peak. I do need to make a peak operation. And then I'm going to make a pop operation. And all the pop is going to do is just going to return the new head of the linked list, and it's going to free the old head. So the pop, it's node star now, I don't like that. All right, so node star, this is going to be the new head. It's equal to the head next value. And I'm not checking for null here because I'm ballsy and I'm brave. Probably will need a null check here. And then what I'm going to do is I'm just going to return the new head. But the thing is, I shouldn't return the new head before freeing the old head. So what I'm going to do here is I'm going to free the old head. Free the old memory. So I should free head. And if I really wanted to, there's two ways I could go ahead and get rid of this head dangling pointer. Either I could set head equal to null here, or I could set it equal to the new head. Either one of these would have been technically accurate and would have been just fine. And then all we do is return the new head of the linked list. Or the stack, I should say. Well, it's the head of the linked list. And the top of the stack. All right, now I'm going to go ahead and make the peak operation. Peak, peak. All right, node star head. And this is like a really simple one. All it's going to be returning is the value, so it should be head dot value, because I think I literally called it value. Did I call it value? I did. All right. So all I need to do is return the value for peak. So this is, the peak operation is probably the easiest one to code up, thank God. And now the insert, or the push. The push is going to be a hard one. So node star push, node star head. And just so you guys know, most people, when they're coding these, like nowadays, I don't know why this is like a common convention. When you perform an operation on a linked list, normally you end up returning the new head of the linked list, so that way it's easy to say, hey, this is my new linked list now. So the push operation will return the head of the linked list. And the pop will also return the new head of the linked list. So it's just like something that's very common nowadays. If you see me doing stuff like this, know that it's just like a convention that most people use, and so I'm trying to teach it to you guys. Hopefully you guys get this by the end of the class. So now what we need to do is we need to create a new node. So create the new node. And normally you want to make sure that your node allocation works, but I'm going to, again, be a little bit ballsy and not do that. So new head is equal to node star. I need to allocate this memory because it hasn't been allocated yet. Allocate one of them, and it's going to be size of node. And now what I can say is, did I call it new head with me? I deleted two characters, cool. All right, new head is equal to, the value is equal to, what did I do? Because I'm like, I need to have an int value and I need to have the node star. Because I need to have the head of the linked list. So old head, and I also need the value to insert. So, all right. Old head, and then I also need the value. So the new head's value is equal to the value that we're given. And now what I say is the new head, when I insert, I always want to insert at the head of the linked list. I want to insert it to the front of the linked list because the front is going to be your top when we're doing the insert at the front. or the stack methods that I talked about. So what I want to do is I want to say the new head's next value is equal to the old head's value, because that's how I get around, and that's how I insert this new head. So all I need to do is next is equal to the old head, and that takes care of inserting this value completely. The only thing I need to do now is I need to make sure that my head is updated appropriately, and how I do that is I just follow the instruction at the top. I return the new head of the linked list. The new head of the linked list is this head I created. So as long as I make sure that I do that, I should be okay, and it shouldn't be that hard to do. Return new head. All right, does anyone have any questions so far on the push operation? Because I feel like the push operation is probably the hardest one to understand. It's French. I'm pretty sure that autocorrect is just messing with me. But anyways, any other questions? Yeah, what's up?
I got a question. So you in the node you have node push. So you're passing in the old head and then a value. What's that value?
The value is the value we're inserting. So we're inserting this value of the linked list into our stack. And so what I'm doing is I'm saying, okay, that value that we're inserting, I'm putting it in here. So that's a really good question. I can go ahead and rename this variable and make it a little more clear. So that's the inserted value. All right, and so now, this is going to be fun. This is the worst part of this code. All right, so we need to go ahead and make the head of our linked list is equal to null. Yeah, we'll do it on the new line. And so what I do is I loop across all the values. So what I'm going to do is I'm just going to say how many tokens we have, and then I'm going to go ahead and output the result again. So I need to read the number of tokens. Int n is equal to nothing. Let me just scan it in. Int I equals 0, I is less than n, I plus plus. So what I do is I read in the token somehow. I'm going to be really nice. I'm going to make it so these are all only one character. But that means I shouldn't do any spaces, so that's going to be really frustrating for me, but okay. And so now if the token is a number, I need to go ahead and turn it into an int and then add it to our linked list. So check if the value is a number first. And so how we check to see if it's a number is really simple. So if token is greater than or equal to the character 0, and token is less than or equal to the character 9, it's a number. And so this is like just a really simple one. You can do something much more fancy with A2I, or you could do integers if you knew that things were integers somehow. But I'm gonna just do something that I can get working immediately, which is why I'm doing it this way. Again, there's more efficient ways of doing this. I just want to show the stack working in action. And that's probably not gonna go that way, but we'll see. So what I want to do is I want to add this, I want to push this onto our linked list. And so how I push it onto our linked list is I say the new head of our linked list is equal to the push of the head and the new value. So token, I can spell token minus the character 0. The token minus the character 0 will actually turn this into the correct integer because the characters 0 to 9 are actually in order, like directly. So this actually is a really dirty way to do it, but that will do what I need it to do. And then this head here will be the head of the linked list, because that's how the push operation works. The push takes in the old head, and it takes in the value that we're trying to insert. So I actually should change this to, and do that, awesome. So this is the inserted value. What I did there was I just hit Control-V because I copied that thing last, so I didn't have to type everything in. All right, so now it's not a value, which means it has to be an operation. So if, else if, token is equal to the plus sign. So if it's equal to the plus sign, then what I need to do is I need to add these two values together and then push it onto the linked list. So I need to go ahead and say int a is equal to head.peak. Oh no, not peak. Peak head. Oh god, object-oriented programming was like slipping through there. But the thing is, I haven't actually removed the element from the linked list, or the stack, so I need to pop it as well. So I should say head is equal to pop head there, and then head is equal to pop head here. Right. So now I have A and B, and now I can form the operation and add them back into the list. So I had say head is equal to push head, and then A plus B. Now, this is really fine and dandy, but does anyone see any issue that's going to happen with this? No, it's going to get both of them just fine, because it's going to grab A, and it's going to pop the value, and then it's going to get B, and it's going to pop the value, and pop that value. So we're going to have A and B off the list, and then we're going to push their sum onto the list. We'll go ahead and, I'll just go ahead and continue doing this, and then we'll see what goes horribly wrong later. Hopefully it's not a compile error, but knowing me, it's totally going to be a compile error. So that's minus. This is going to be multiplication. I'm not going to do exponents because exponents are for chumps. Alright, so that's everything I need to do. And then what I need to do is I need to return the result at the end. So what I'm going to do is I'm going to do print f %d, and then we're going to do head, peak head. And then what I should do is I should probably, just to get rid of all the memory, I should pop my head. So let's go ahead and come up with a real quick example of something that we can add together on the .cam, and then we'll do something with. So we'll have, let's do 7, 3 plus, why not? We'll do, so that's going to be one of them. We'll do 5, 4 minus, and then we'll multiply these two together. So what should this end up being? 10. This is going to be 5 minus 4, so that should be 1. Then times these two together, it should be 10. So it should be 10 for the end. So it's going to be 7, 3 plus 5, 4 minus star. And again, this is only going to work because I'm not going to put any spaces, and I'm just doing single characters. So let's see if GCC works on this thing. Probably should have checked that first. Wow, that's not good. All right. So 7, 3, you can't see. You guys are like, why did he say wow? All right, it compiled them the first time. That's why I said wow. All right, 7, 3 plus, 5, 4 minus, and then star. Awesome. So let's go ahead and find out what happened. This is good. I mean, it's not good, but it can show me use my Valgrind skills, which is something that you guys should all, oh no. Valgrind, and then we're going to do a/a.out. And now we're going to do 7, 3, oh, I know what I did wrong. I'm supposed to enter in the number of tokens first. So the number of tokens is equal to 7. And so I should have done 7, and then 7, 3 plus 5, 4 minus star. And I forgot a new line. Also, that was very wrong. Why did I Valgrind it again? I should have GCC'd first. All right. So we're going to GCC./a.out, and then we're going to do 7 values, 7, 3 plus 5, 4 minus star, and then -1. So this is having a lot of issues aside from the fact that we're getting -1 instead of the other thing we needed. So let's go ahead and output what's going on so that way we can see where things are going wrong at. So I'm just going to go ahead and print f Now we're pushing something onto the stack here. So we're pushing the right values. We're pushing 7, we're doing 3, we're doing 5, we're doing 4. Maybe we're pushing the wrong value here. So I'm going to go ahead and output whenever we're pushing one of these things. So we're going to do A plus B. We're going to do A minus B. We're going to do the multiply. And then we're going to do the divide. And then we can go ahead and compile this. We can run it. I said we can run it. And then we do 7, 7, 3 plus 5, 4 minus star. And so it pushes 7 and 3, and then it pushes 10. Why is it pushing 10? 7 plus 3 is 10, and then it pushes 5 and 4, and then it pushes -1. Why is it pushing -1? It's doing 4 minus 5, and the reason why is because it pops A first, and then it pops B. And so it's popping A, and then it's popping B. So A is 4, and B is 5, which means it does A minus B, so it's going to do 4 minus 5 instead of 5 minus 4. So we actually need to reverse the operations of all of our things. And then what's worse is multiply isn't even working at all. So that's another can of worms there. Let's see. Look at that brain. All right. So this isn't working. All of these need to be inverted. B and A. This needs to be A here. This needs to be B here. The multiply, the order of the multiply shouldn't worry. The one that we should worry about is the subtraction as well. B, A, this is going to be A, this is going to be B. So this is like a common mistake that people make when they're doing it, which is what I was kind of trying to hint at when I was saying, is there any problem with this operation? And the answer to the plus was no. The answer to the minus is yes. So let's see. The multiply though isn't working, which is a little concerning. Let's go ahead and just print out what the token is as well. Printf %c, comma, token. And then hopefully everything works out fine. 7, 7, 3 plus 5, 4 minus star. Great, I forgot the new line. It's not getting to the last one. Did I increment I somewhere on accident? No. Oh, that is really bizarre. Yeah, so this looks terrifying to me. I'll worry about that later. There is one more thing I want to talk about, and I'm not going to be able to do the full thing. So then the question becomes, how do we get these expressions from a how do we get this postfix expression or the infix expression? And there's a way to do so using a stack as well. And so how you get the postfix from an infix, what you do is you keep track of, so inside evaluating postfix, we keep a stack of operands, and here we keep a stack of operations. So keep stack of operations, and then what we do is we, when a operand is encountered, output operand. That's step 1. Step 2, when operation is encountered, and this is not in parentheses, operation, we pop operations on stack until a lower precedent operation is on top, or a paren is on top. Then push operation on stack. And then the last step, I know this is a lot to take in. I'll probably end up doing an example next week just to show it work in use before I move on to DQ lecture. The last one is when a open paren is encountered. Actually, yeah, open paren is encountered. This is not the last one because I just realized there's 3 and 4. All right, push open paren on operation stack. And then 4, when a close paren is encountered, you pop and print all operations on stack until a open paren is on top, pop, open paren. So this means you don't end up printing the parentheses at all. You just pop until you get to one, and then you pop it. And so this is like really confusing, and don't worry about understanding this right now. I'll upload these notes so that way you can look over them, think about them for a little bit. What I would recommend doing is trying to turn some simple equations into postfix operations. So try doing like 3 times 4 plus 7 divided by 8, and then do 5 plus 1 minus 2 plus 8 divided by 2. And so see if you can convert these into postfix, the expressions, and then what we're going to do next time is I'm going to do these, like just to show you how they work, and then I'm going to do some parentheses ones as well, because they can get really complicated. All right. Anyways, I hope you guys have a nice day. I hope you guys had a good weekend. I know that probably